good. Have a good day on Monday. Yeah. Got a little cold on us. Feels good. Open up the windows. Get the hot tub nice and hot. Like Swede. Question? Questions? Questions, Michael? Hey, got a question. Got a question over here. A little louder, a little louder.
I just want to know why, because it's SP2, the one pair's the SP2 instead of SP3.
Which one?
Number 3.
What page? 2. Number 3 on page 2. This mechanism, you're referring to the key, and I protonated that oxygen and not this one? Right? Okay. These lone pairs, what type of orbital are they in? The upper oxygen. Lone pairs are in sp2. Lone pair here. Well, there's 2 lone pairs there, but what's the hybridization? What? Maybe since there's 2 lone pairs, you may question it. One of those lone pairs on this oxygen here is in what type of orbital? P orbital, yes. And if you draw a resonance structure, what type of partial charge is on this oxygen? Partial positive. And if you draw a resonance structure using these electrons, what type of charge is on this oxygen? Partial negative, draw resonance structures. So which one is more likely to react with H+? The partial positive oxygen or the partial minus oxygen? Partial minus oxygen. Also, Kingsley, once you draw the protonated species, if you protonate here, you cannot show any resonance structure. If you protonate up top, you can show a resonance structure. So would you rather show a protonated species that you can show a resonance structure of, or one that you can't? You'd rather be able to show a resonance structure. That means the species that you're drawing is more stable. A variety of reasons why the top oxygen is more basic. Okay, time to get started. Any questions about lab this week? Somebody left the eyeglass case? Yay, no? We do have a handout today. I sent you one by email about alcohol oxidations. This is the outline on colored paper. I'll do 2 stacks, same thing. Actually, I think I've already got a couple. Any questions about lab this week? Any questions about guidelines for notebooks? Guidelines for reports? Anything like that? Question?
I had one question. When are we going to finish AMR lecture?
Not quite sure. My first thought is we'll probably finish in here whenever we can get to it, as on the syllabus. We also have, no, that's not right. We were dealing with reactions of ethers. I think we're on the last page of that handout, and then we'll move on to epoxides. You should print that out yourself. Green sheet is kind of an outline. Ethers is blue, I think. Yeah. We did the first one in class. I don't believe we did the second one, did we?
No.
Okay. How are we doing? Brittany, how you doing? Are you doing all right?
Yes.
All right. Let's see how we did on these. Treat this with HBr. What's the primary reaction of ethers that we're doing here? Alkylation or cleaving them with HX. Okay, product here I would probably say is going to be how about that? Question?
Yeah, so you use this secondary over the primary, it's more stable. Why is that SN2 and not SN1? Because it could do either. Or is that just a rule you prefer SN2?
Well, it is sort of just a rule, a statement up there. Okay, mechanism here, what's the first step? Okay, we've done this before. Protonate, okay? I assume you can do that mechanistically. All right, we got a Br minus. We have two different, the leaving group is attached to two different carbons. The protonated oxygen is attached to this methyl, is also attached to this isopropyl. What type of chemistry are we going to do? Ultimately, it's a substitution when you do the dealkylation and the cleavage. Well, the statement up there said, if a tertiary reaction site is present, always go SN1. If no tertiary site is present, go SN2. Do we have, is either of these tertiary?
No.
No, so what are we going to do?
SN2.
SN2. That is the statement that I'm making. A lot of times you get mixtures here, but for the purpose of us, so we know what to look for, that's my statement. Some textbooks will tell you another statement. So we're doing SN2. Since we're doing SN2, are we going to attack the methyl or this carbon over here? Right or left?
Right.
SN2 is largely governed by, starts with an S, sterics. So SN2 is going to do further attack over here, kick the oxygen off of that methyl. Br now binding to the methyl, the leaving group leaves. Br binding to the methyl. How about your leaving group? But your leaving group is ultimately an alcohol after it leaves. So according to our rule, we did SN2 and we attacked the least sterically hindered carbon of the two choices. Questions about that? Warren, how are we doing? Next one. I would say, do we need to turn these answers in? I don't like collecting work. I assume you're doing the work. And then we're going to get the answers here, and we're going to ask questions and see if we get wrong or confirm. Phenol plus ethyl iodide. Protonate the oxygen. I minus. Okay. Here, there's really no choice. Okay? That's primary. What is this over here? It looks like it might be tertiary, but it's really not. Okay? It's not an sp3 carbon. You do not do SN1 or SN2 on an sp2 carbon. You can't do either, nothing over here. Right? You don't make cation on sp2 carbon. You don't do SN2 on sp2 carbon. No chemistry over here. There's no choice. The only thing you can do is attack here, kick off the oxygen, I bind to ethyl, leaving group leaves. That's what we get. And so you cleave this ether to the phenol plus the alkyl iodide. How we look? How we do? Looks pretty good. What did we do up top in the example reaction? What mechanism did we do up there? Did SN1. Why? We had a tertiary site available. And so from the protonated, what did we do? It ionized, make tertiary cation, and then that BR attacked tertiary cation and give it SN1 substitution. That's because tertiary cations are so easy to form, the ionization will take place almost instantaneously. So that's sort of the rule we're doing up there. We'll do some more down here, but these will be cyclic. Cyclic ether. Okay. The oxygen can be in the ring. The oxygen is part of the cycle here. We can protonate this. Got Cl minus. That's primary. This is secondary. What are we going to do?
SN2.
SN2. SN2, we're going to attack left or right. These spherically hindered, so we attack here. Kick off the leaving group. What does that give? Well, it's just going to give one molecule instead of two. Because the leaving group is still going to be connected to that carbon over here. What do we get? I'm going to try to sort of draw it just like this. What's now bonded to this carbon? So we call it cleavage. Really, we could say opening. It didn't really cleave it into two fragments, but opened up the ring. We did cleave the ether. It's no longer an ether. Did we do any chemistry over here at this carbon? No, so there should be no change in that carbon in terms of stereochemistry. Now, everything we've done, we've really assumed one equivalent of HX. You could actually come in with another equivalent of HX. What if we reacted this with HCl? What could you say would happen there? Well, we got an alcohol. Do alcohols react with HX? Yeah, that was like the first reaction we looked at last week. If this could theoretically react again, we could protonate Cl minus if we sort of stick with our rule here, I mean, it's not an ether, but if you want to replace this leaving group with chlorine by what mechanism? You could theoretically do either because it is secondary. I would probably do SN2 though. Again, it could be either. I'm going to do SN2, kick off the water. What are we going to get? we're going to get inversion. So let's see here. This is oxygen. H is in the back. O carbon with carbon methyl. That's S. So they should have R here. I'm going to put the chlorine here. To make this R, what do I need? Bold or dash for the methyl?
Well, you can do bold on it.
I actually need bold. So now chlorine, carbon with something, and then methyl. R. Get that. Where S is inverted to R. Because what mechanism did I do here to get the chlorine on? Another SN2. Okay? See, some of those alcohol products up there could have theoretically reacted with HX again. Sort of assume one equivalent unless you're told excess. Ultimately, you sort of need to clarify, is this one equivalent or two? One equivalent, you have to stop here. You need two equivalents to do it again, right? Two molar equivalents. Of course, here you also generate water, which was your leaving group for that SN2. All right, let's do the next one. Do this on your own if you haven't done it already. Protonate. Okay, we're going to do SN1 or SN2.
SN1 is a resin.
Varsha,
SN2,
why SN2?
because it's not a secondary carbon on the other side, because you don't, so you have to go the other way.
Primary, secondary? Okay. Anybody have an argument? Jordan?
It's a resonated secondary, so it's as good as a tertiary.
Yeah. A secondary that's resonance stabilized is just as good as a tertiary or even better. Okay? I would do SN1 here. Leaving group leaves. And we get we'll draw out this benzene ring. We made secondary cation, but it's resonance stabilized. What do you call that position next to the benzene ring? Benzylic. It's a benzylic cation. That's probably better than a standard tertiary. If your cation is resonance stabilized, it's going to bump it up at least a notch in terms of primary, secondary, tertiary. Now we can come in, now the Br minus. Come in, what do we get? I'm going to draw this out, just sort of zigzag. Boom, 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 boom. 1, 2, 3, 4. 1, 2, 3, 4. Boom. Phenyl. Br. We have a carbon. Is this RS? What is this here? That's racemic because how do you attack cation? That's planar. You attack it from either side. Your book does discuss how whenever you do a cation, you may get a slight amount of inversion. I've never discussed that with you guys. Not all books take you into that. For us, your cation, what do you get? Racine. Questions about that outcome?
Yeah, why don't you open up that ring?
Which ring?
That's the ring with the ether in it. You like open it.
Right here?
Mm-hmm.
Well, the leaving group left.
When it was first.
Protonated, and then it left to make cation.
I see.
Right?
Right.
That's essentially the leaving group.
Yeah.
But it really didn't leave because it's connected by the chain up there.
Got you.
I mean, just down here. I mean, we opened this one up, right? Okay, down below, that's THF, common solvent. You put two double bonds in, that's known as furan. We'll see furan during test 2. How do you get to that molecule there? You have to have an H here, H here. You have to add 4 H's. 2 H's here to get rid of the double bond, 2 H's here to get rid of the double bond. 4 H's. What do you think THF stands for? Tetrahydrofuran. Yes. It's a common solvent. It's an ether solvent. What if we react it with a strong nucleophile? No H plus. Strong nucleophile, such as maybe in-butyl lithium. That's a pretty darn strong nucleophile. Of course, with most strong nucleophiles, you can't have H plus. If you put H plus in here, why would you want to try to put H plus in here? Protonate the oxygen?
No.
It reacts with lithium.
It'll react with in-butyl lithium. You can have your cake and eat it too. Okay? There'll be no reaction. Basically right here, ethers are unreactive under non-acidic conditions. In all these reactions, what's the first thing we did in the mechanism? Protonate the oxygen. That makes the oxygen a better leaving group. It can then leave and do the chemistry, either SN1 or SN2. You have to decide. If there's no H plus, you can't do the reaction. Use a strong nucleophile, you can't use H plus because these will react. So if you're using strong nucleophile, by default, it ain't going to do anything. Ethers are good solvents when you're using strong nucleophiles. They're unreactive towards strong nucleophiles. So like THF and diethyl ether, very common solvents, especially when you're doing like basic conditions. Question?
If you use the tosylate, could you cleave the ether?
If you use what?
That tosylate, to like convert the O to OTOS, can you cleave the ether?
And you can't really convert this to a tosylate because that's just an alcohol reaction.
Oh, okay.
You make a tosylate, you lose the H from the alcohol. Yeah, you can't really make a tosylate. You see what you're getting at there. Because with alcohols, that's the way you can do it, and then you use strong nucleophile. Okay. Now, this is most ethers. When we get to epoxides, this will not be the case. What is this? Oxide. More generally, what is it? It's a cyclic ether. Okay? And it says here ethers are unreactive. Okay? Well, this is a different case. This guy will be reactive to strong nucleophiles. This guy's going to be reactive to just about anything.
Is that because of bonding?
That's because of the bond strength. Question, Cassandra. Bond strength. Seems like a good point, good time to move on to the epoxide handout. Get rid of that, will ya? Oxides. In organic 1, we saw synthesis of epoxides from alkenes. What reagent did we use? MCPPA, which is a peroxy acid. Epoxides have lots of applications, including biochemistry, synthesis of leukotrienes. As you slept overnight, your body made leukotrienes involving epoxide chemistry. All right. And from here, this leukotriene can react with nucleophiles to give these products. Okay. Eventually, want to be able to do and understand this chemistry. First thing, let's review synthesis. Reaction of an alkene with a peroxy acid, such as MCPPA. You know the structure of that. Should be in your textbook. Notes from Organic 1. I'm showing a variety of solvents, dichloromethane. What is that? Oxygen with 2 ethyl groups. Diethyl ether. That's just an abbreviated form of showing diethyl ether. What is that? DHF, cyclic ether, common solvents for lots of reactions. Okay, this is going to give this epoxide. It's going to be racemic. As we do, it is a chiral molecule. This give this. Well, that's not chiral. We have a plane of symmetry. You can show that dashed or bold. It's the same compound. Down here, no plane of symmetry causes the methyl. We're going to have racemic. Of course, if this is not optically active, then your product mixture cannot be optically active. It has to be racemic. Now, your book will talk about the Jacobson enantioselective selective synthesis of epoxide, Jacobson epoxidation. We're not going to be covering that. Take a look if you want. Okay. Another way to make epoxides. We know this chemistry. We can put it together to have another way to make epoxides. If you react an alkene with bromine and water, what type of product do you make? That type right there. What is that type called? Halohydrin, right? Halohydrin. Okay, Br is going to be on the end, the OH here. If you don't know this reaction, please review your alkene reactions. You'll see alkenes on the final exam in this course. Okay, halohydrin. Now if you take this halohydrin, let's just use sodium. What is sodium going to do to this?
Redox.
Redox. It will make the minus here. And form hydrogen, etc. Okay? Now this minus will, boom, do an internal SN2, and what does that give? The epoxide. That's just an internal Williamson ether synthesis. Now, you can use sodium hydroxide here. Most alcohols, sodium hydroxide doesn't work. It actually works here, but it goes against what we've said, okay? That is another way to make ethers from halohydrons, internal displacement. Yes, there's ring strain. Why is this able to form? It's ring strain, but it's like, it doesn't have to do much in terms of entropy. It's like, there it is.
Byproduct for that, NaH?
No, my product would be NaBr minus. Plus, what's the other thing? No, there's no water here.
Hydrogen gas.
I'm using sodium,
H2.
H2. A sodium reacts with alcohol to make H2 plus the sodium alkoxide. Then when the oxygen here, then you have a sodium plus and a Br minus. Okay. Mainly review, standard chemistry. Now we see we can make epoxides that way. Lots of reactions of epoxides. First we'll do under acidic conditions. And under acidic conditions is going to be just like what we did on the previous page. And we're going to have the same statement. When we have a tertiary reaction site, go SN1. If no tertiary site, go SN2. But with epoxides, we have something unique in terms of stereochemistry. SN1 with epoxides gives inversion. That's different, right? Usually SN1 gives racemic. Why does it give inversion? Somebody tell me. Very good. Because of significant back bonding. We'll explain that. It's actually a blend between SN2 and SN1. We'll actually refer back to, remember bromonium ions? This is a three-membered ring with a positive charge with bromine. Okay? It's actually very analogous to that. All right, using HX. Well, if you're under acidic conditions, first thing you're going to do is protonate something. So let's do that. Again, I'm not doing the mechanism for protonation. I assume you can do that. Question?
How should one be forward and the other one not be? Since it forms a ring, I thought both.
You mean here?
Yeah, the one to the left. I thought it would have to be forward as well.
Perhaps. It's just like if I drew methane on the board and drew it like this.
Okay.
You know that it's really tetrahedral. It really doesn't matter over here because that's not chiral.
Okay.
So yeah. But it matters over here because that's chiral. So I need to show something over there. And I'm showing specifically that it's a RS.
Okay.
Yeah. Okay, we got Br minus. Are we doing SN1 or SN2? That's primary, this is secondary, so what are we doing?
SN2.
SN2, because we don't have a tertiary site. Since it's SN2, which side are we tagging, left or right? Left. Kick off the leaving group. We're doing SN2. What do we get? Boom, boom, boom. Br is now attached to the end carbon. Oxygen leaves. Which carbon is the oxygen still bonded to? The first one or the second one? Second one. This one. Now that one, that's the one it left. It just opens up and it's here, and this is OH, and it's folded. Did we do any chemistry of that carbon? No. No, so it's still bolded. Basically, the oxygen's forward. It's also forward on the other carbon. Okay. When something kicks it off, boom, kicks it off. It's still forward. It's just no longer bonded to that carbon. Still forward. So that's your product by SN2. And really, there's nothing new there compared to the ether sheet, is there? Question?
Yeah, I have a question. So if you look at the chirality of the second carbon in a reagent, isn't it, it's R, right? And then,
Let's see.
the
Let's
product
see.
is Ed.
Let's see. This one here is
It's on.
R.
It's on.
Oxygen.
okay, here. Let's put in the H. The H is going back here, right?
Yes.
Okay. Oxygen's 1. Carbon with carbon or carbon with oxygen is 2? Carbon with oxygen is 2. 1, 2. Carbon with carbon 3. It's S, H in the back. Okay? Let's see what this is. 1. Carbon with bromine beats carbon with carbon. 2, 3. H in the back. What is this? S. But see, inversion doesn't mean you always go from R to S. Because what you just got at is, if your priorities change, you can start with S and end up with S, and it still have inverted. But we call it S because the priority changes.
Yeah.
So, usually, that's a very rare thing, though. For example, if the nucleophile was H minus, and we did the same chemistry, and that was an H, would that still be S?
No.
That'd be R.
Yeah.
But we didn't do any chemistry there. It only changed because of our priorities changed. Okay? But 99.9% of the time, we can just say R to S because usually we don't ever see that. So that's what you were getting at. All right. Next one. Here we go. Now we're going to have to see what, this is going to be a little bit different. How are we doing, Sadi? Protonate. I mean, what else would you do? Protonate, right? Runner city condition. What you want to do now? We got secondary up here. Tertiary here. What do you want to do? SN1. SN1 means what's going to happen next? Does leaving group come in here and kick that off?
No.
No. Ionization. Leaving group leaves, so it leaves this carbon. What do we get? That opens up. Just a methyl here. And that is a plus. So we just ionized. No change here. This oxygen's forward. Okay? When this bond breaks, okay, it just disappears. Really, the electrons move there, but I can't do that. Okay. The bond breaks. It's still forward. It's just no longer bonded there. Still forward, it's no longer bonded here. This is trigonal planar. So there's nothing forward or back. Everything's in the plane because it's sp2 trigonal planar. All right? What's the final step? Forget about the rule up there. Just organic 1 mechanisms. Final step 1. This attaches here, and we would say from organic 1 maybe, this is bolded. What's that going to be? Racemic. But with epoxides, you don't get racemic. That's because this leaving group has really not truly left and like moved way away and become insignificant. These are electrons. Do you think it's attracted to the plus?
Yes.
Yes. Significant interaction. Between the electrons and the plus. What else can we call that? Starts with a B and a B. Yeah, significant back bonding. So, let's say here's the cation. This oxygen used to be bonded to it. We say it ionized away. Does it really just move away and leave it free? No, it still is sort of there. Because pluses like minuses. Now we're saying it's not bonded to it, but there's some attraction there. And your book will kind of show it, sometimes bonded, sometimes might call that resonance structure, but that's not resonance because we're dealing with a sigma bond. But it's still kind of liking that plus. It's still in the way. It's still blocking this side. Okay? So you try to attack the cation. Can you attack from either side? Can you attack from this side?
No.
See, I'm sort of in the way here.
Now I can.
See, the leaving group is kind of still in the way. It's not fully bonded. Now, every book will show this kind of differently. We can kind of like say, now this comes in. Now I'm going to call this backside. Now backside doesn't mean it's coming from the hull necessarily. Backside means it's opposite of the leaving group. And if the leaving group is forward interacting, it's kind of like this. It's forward. How are you going to come in?
The other side?
Coming from the backside, or the other side. Okay? And what do you get here? You end up with that chlorine predominantly coming in from the opposite side. It moves the methyl forward, and you actually get inversion with SN1. Kingsley.
Is the same thing that happen with cyclical ethers, just like the...
I have a hard time hearing you, Kingsley.
Does the same thing happen with like cyclical ethers, just like the stereo decides to change?
Like we did on the previous page?
Yeah, like...
It tends to not happen only with epoxide. If there's more carbons between here and the OH, it typically doesn't happen. It can still be connected, but if it's 3 carbons in between, it's far enough away. Yeah, of course, there's a gray area in between. But what I'm saying is, you only get this crazy inversion with SN1 with epoxides. Now, why not just keep it bonded there? I mean, why not just attack here and kick it off and do SN2? Wouldn't that get the same product? Ah, you don't do SN2 on tertiary. And we said if you're going to do SN2, which carbon would you attack? You attack the top if you're going to do SN2. So it's sort of like, well, it looks like SN2, but I'm attacking the wrong carbon. Well, it looks like SN1, but I'm getting an inversion. A lot of books say it's a blend of the two. But it actually is very analogous to this here. When we made bromoniums in organic 1, and then either like a Cr minus or another Br minus came in and attacked, which carbon did we attack?
Bottom one.
Actually attacked the bottom one. We attacked the more substituted, kicked it off. Now when we did that, we didn't call it SN2 because we haven't done SN2 yet. But that is an SN2. Well, it's really not. It looks like it, right? That's what we did in organic 1. Doesn't that look like an SN2? But guess what? If you were doing SN2, you should be attacking up there because that's the least stereo-coherent site. And really, this is the same type of thing. Didn't we say how when we do this, then this starts like breaking? And would you rather this start breaking or that start breaking? That would rather start breaking and we get some plus here. me showing you that starting breaking looks like that. Look at the similarities between a protonated oxygen in a three-member ring versus a protonated bromine. The only difference is this is only with tertiary. If this was primary, if you're doing SN2, which would you attack? Top. Where with bromonium, you never attack the top. So there's a discrepancy there. All right, let's do some nucleophiles other than X. What about H plus in water? Sure, it's the same thing as HX, except nucleophiles water. By the way, while I'm thinking about it, in the back of this handout, there's a puzzle. Remember, we're getting one, I give you a puzzle of alkenes. Here's an analogous puzzle about epoxides. There's a riddle. Was the sodium atom certain that he had lost an electron? You get the answer down below. They gave you the number 10.
Is it possible?
Okay, H plus with other nucleophiles. First off, strong nucleophiles can't be used under acidic conditions. So we couldn't say H plus in lithium. That doesn't make sense. But we can do H plus in water. This is H plus in water, right? Aqueous strong acid, H plus in water. What are we going to do first? Protonated epoxide. What's a nucleophile?
Water.
Sulfate, not going to be a nucleophile in this class. Water. Okay. Primary, SN2 or SN1?
Two.
Primary over here, secondary there. There's no tertiary site, so we're not doing SN1. Doing SN2. Attack left or right? Attack here. Kick that off. Boom, boom, boom. That's bolded with an OH. That was your leaving group. What's now bonded here? Water. We have not lost the H magically. What's the minus at this point? HSO4 minus. What can take the H? I'm not going to draw out Lewis structure. I never really have. Electrons take the H. These take the 9. H2SO4 reformed. So the acid is a what? Catalyst. See, when you look at this, this is H plus and water. Or you can show it as, what's another way to show this? Okay? 3 different ways to show it. I could probably show it another couple of different ways.
I was going to assume that our acids are aqueous.
Not necessarily. I mean, HCl can be dry. HBr can be dry. Sulfuric acid can't be. So you have to make sure. If you're using HCl, you would need to clarify. There's water there. Now I could have used water to take this. That would have made H3O plus HSO4 minus. That's more strictly correct because that's how it exists in water. Again, I like to reform the actual acid. So what do we actually add to this We added water, but it was catalyzed by acid. Okay? Because water's not going to add unless you protonate. Okay? Read the second statement. Weak nucleophiles require protonation of the epoxide. Instead of water, what about methanol? Protonate. Got acid to protonate. Now there is water here, that is an aqueous acid. But this only requires a micro drop to be a catalyst. And a micro drop of water is not going to be enough. If you do it in a huge amount of methanol, methanol is going to be your nucleophile. Okay? So now methanol attacks which carbon? Top or bottom? Doesn't matter here. Symmetrical. Okay, what mechanism am I doing here? SN2, it's a secondary. I was wondering if I needed to do the back bonding thing, but no. That opens up bowl. The methanol is going to be what? Going to be back, because it came in backside compared to the leaving group. And then the HSO4 minus can take the H. These electrons stay behind, and you get right there. By the way, some terminology back up here. When the epoxide essentially reacted with water, what type of product did we make? Diol, yes. Yes, diols are, that's an important class of compounds. Reacting in epoxide with water, when you open it up, you get a diol. Okay, what's wrong with this reaction here? Why is this not feasible? You cannot have a strong nucleophile, a carbanion with acid. These two will just react and game over. We will move on to basic conditions. But guess what, guys? Under basic conditions, the mechanism is always SN2. See some of you tomorrow in lab. We're always meeting in lab unless otherwise told. Have a good day, guys. Please look ahead.